really generative models, which have now found that we were testing on this holdout that was found on GitHub. So there's already instances where our notion of leakage is very common, and we have to think about what do we care about, and how do we make sure if we care about in-distribution generalization with a traditional test set, we have to make sure it's not contagion with the training. But if we care about zero-shot, we have to think about, does that jeopardize some of the notions? So for example, multilingual work, which came out in December, only tested multilingual zero-shot and showed improvements. But there's 100 languages, and so on the individual languages, there may have been deterioration, even though you saw improvements on the zero-shot. So I think there's actually an active question in our field right now. Yeah. I don't know if you have thoughts about it, but maybe.
I have doubts, like, about how the field is doing, I guess, but this is very helpful.
Yeah, yeah.
We have time for one more question.
Hello, so yeah, great talk. My question was regarding the compression of the models. I mean, thinking especially on the fact that this is something that's been happening a lot, right, to put models into the mobile devices, and you mentioned that they tend to worsen the biases and stuff like that. So my question was, what kind of distortion metrics do you use when you compress a model? I mean, if you want to take that into account, like the biases and fairness.
Oh, yeah, this is interesting. So yes, there has been work on constraining pruning methods or distillation methods to better reduce the impact of this. So for example, even with distillation, Serena Wang did a paper, I worked with her on a paper last year where she's showing combinations of teacher-student objectives that lead to better outcomes. And I think part of it is that it's underexplored. So because we've only been optimizing level of compression with respect to top line, there's just been less work on adding additional constraints. But the work so far has been very promising. So turns out we have quite a bit of undersaturated exploration area where we can still achieve very nice compression rates, but achieve better distribution of error. So yeah, but typically it involves adding another objective. So pruning is done often iteratively. So you introduce it slowly to get to your final size. So you would add an objective there to kind of spread the error. With distillation as well, during the optimization process for your smaller distilled model, you can add another objective to penalize if it's disproportionately impacting the worst case group.
Okay, so my last question, maybe a little.
Nice, good. You're sneaking in another one.
Just
good.
one. I had to. Yes, I'm sorry. Now, just about using sparsity to compress a model like that. Usually, sparsity is not a good thing to compress stuff because you need to describe the supports, which is the largest part.
Yes. So this is an excellent grumpy question. So sparsity actually doesn't play well with our current hardware. So a lot of researchers study sparsity because it achieves the highest levels of compression. And a lot of researchers are optimistic that the next generation of hardware will catch up. But structured sparsity does play well with current hardware. It just doesn't achieve as high compression rates. But this is an important point, which is that right now there's a hardware gap. So our current hardware doesn't support unstructured sparsity. And researchers are kind of betting, okay, the next generation will. But unfortunately, I just talked to some hardware architects, and it seems like they're not quite sure what the timeline is. But there are some types of sparsity supported, like 2x1 blocks on the new NVIDIA hardware are supported. But you're right, it is a hardware algorithm incompatibility. So for someone actually deploying in the real world, distillation is more common, quantization is heavily used. Quantization has similar impacts on fairness. So these have similar threads.
Okay, thank you.
Yeah, thank you. Oh, okay. Oh, I don't know.
Well, in fact, we started 5 minutes later, so we can take one more.
Okay, excellent.
Yeah. Is there a mic there, or do I have to go all the way?
No, I got it.
Sorry.
So, first of all, I am a Uruguayan, so by construction I would disagree.
Okay, great. Great.
Uruguayan would say, no, you're right. So I would disagree with the person here in the front that said that we should be demanding more fairness. I think we should be thinking of what do we mean by fairness as a collective group, because at the end of the day, anything can be fair or anything can be unfair as long as you prove it. For example, just to give a simple example, there's an essay there was a problem with giving banks, bank loans, right? Which is a problem as old as giving bank loans, which is before neural networks. And a guy who won a Nobel Prize in the 90s said that it was fair not to give loan banks to black people. He he had an argument, and this argument was utilitarian. And his utilitarian argument is the same argument that you find when you go to a subway station and you see a place where a person cannot sleep. And nobody says, hey, this bench is unfair. But the argument is, no, the subway is to take a subway. I don't want people sleeping here. And I have never seen a person going to a bench and kicking the bench for being unfair. So my point is, we should define what fair means. Fairness is at the very beginning, and then look at works like the ones that you're doing that show the types of fairness that we get with the types of reward that we write down, and then think what is fair and unfair.
Okay, now we run out of time. So, do you want to answer something? I think this is a very interesting discussion, and there's plenty of time to keep discussing it.
Yeah.
And I'm very happy that Sarah brought this energy on the topic so that people will keep talking about it. But I have to keep my role as a chair of this session. And just if you have a minute, if you want to respond something.
I agree. I think that's one of the challenges, this notion of universal. Right now, I think I would say we're doing poorly at even following what is nationally protected. So if you think about the amount of fairness research has been on U.S. protected attributes, legally protected, I think there should be more on legally notions of what should be protected, and those are typically inherent properties of us as humans. Like we're born, we grow old, so notions like our gender, our age, that are immutable, those are typically the protected attributes that people think that shouldn't count against you in terms of how you're treated by algorithms or by other humans. But I do agree that this notion of the power dynamics, things like the history of a place, caste, tribe, this changes place to place, but it's also something which impacts people's lives. And so I like to think we should start there in creating more flexibility. And also, I think it's also a core machine learning question, which is how do we create models which can adapt to different distributions and different constraints. But there's no denying that this is the challenge. There's no universal perspective of power, right? We're humans, different power dynamics exist in different places. And I think what's unfortunate about fairness research is that it's been so centered so far on a certain lens, which has been a US legal lens of fairness. So we need more conversation about this. Yeah.
So, great question. And
Excellent.
We'll go to
Thank
the
you.
next talk.
Thank you, everyone. That's amazing.
Please don't leave. We have the sponsors talk now. Okay. The music, turn down.
Hi, everyone. We're about to start our next sponsor talks. So the first of our sponsor talk is Martín Alcalá Rubí from Brain Logic AI. Martín is an Uruguayan entrepreneur with 15 years of experience in the field of AI. He is also an angel investor and holds a dual degree in telecommunications and electronics engineering from UDELAR. He previously co-founded successfully AI companies such as Tyro Labs in 2009 and Monkey Learn in 2014. In 2019, he received an award from the Association of Uruguayan Engineers for his outstanding contribution to the business development of Uruguayan software engineering in the US. Currently, he is the founder and CEO of Brain Logic AI, which he will tell us more about in a moment. Please, let's welcome Martín.
Thank you so much. Just 1 second. Can you help me here, please? Whoa. Can you hold this for me? Thank you. Good afternoon. How are you doing today? It's been a pleasure to be here with all our friends and colleagues from all over Latin America and the world. So my name is Martín Alcalá Rubí. I'm one of the co-founders of Blending Logic AI, and we are super happy to be here and to be sponsoring this event. So the first thing that I want to do is, I want to express all the gratitude and how happy we are as a country to have an event like KHIPU here. So we want to thank to all the organizing teams, all the sponsors, all the people that make this possible, all the people that travel to Uruguay to make this possible. So big hands of applause for this event, please. This is a truly amazing conference, and we are super happy and honored to have you here. I don't know if you have noticed something strange in the sponsors and supporters of this conference. It's the first time in my life that I see a rock band. Yeah? Have you seen any rock band in a conference, in the supporters? I've never seen. So, we are lucky enough that one of the biggest bands in Uruguay, can I tell it, Pablo, or I'm not sure? Okay, let's leave it there. But we have the support from one of the biggest bands in Uruguay. Yeah, they played for, that photo there is from the last weekend. They played for 100,000 people. So, and they are making it to KHIPU at a mysterious time. All right, come on, give it up. Completely honorary to support the event, the education, and the spread of AI education. So that's quite remarkable. And when you see them at a mysterious time, please say thanks, because they charge no money to come here. So that's one of the more evidence that's how important for us in Uruguay and the region is this kind of events. So my name is Martín Alcalá Rubí. I've been lucky enough to be co-founder of Trial Labs, Monkey Learn, and UltraDrop. There are 3 companies. Yesterday, with Trial Labs, we've been honored to release Temporian and to have the visit from our friends from Google Zurich. So we are becoming contributors of this time series forecasting library. So we want to thank a lot to Richard and Matthew, who made it all the way from Zurich to Uruguay to do a call come together with us. So please, a big hands of applause for them. This is incredible, so thank you. The last year, one of our companies was also acquired by a US company. So we are super happy, to keep creating value over the ecosystem. So yeah, so the title of the talk is, would it be possible to create AI-first product companies that reach massive scale from Latin America? We have 5 minutes to discuss that, all right? So why is this important? Technology industry is one of the most important sources of socioeconomic mobility in emerging economies. So for us, technology is not keeping up to date to the trends. It's not losing competition to other companies. It's a matter of creating mobility in our socioeconomic space. So saying it differently, there are many people in Latin America that elevate their socioeconomic status through working in technology companies. That's very important for us. One of the biggest differentiators of first world economies is that create intellectual property. That's another very interesting point. And another thing that we suppose is that AI-derived products will probably lead the most significant technological advances in the next decades, and probably in the human history. You may know this guy, Sam Altman. So he says that he feels that this is one of the most exciting times to create AI companies in years. So back when we started 14 years ago with Trial Labs, it was so early. And I have this feeling that I'm having now that there's a world of opportunities, with all the advance of large models, with all the advance of generative AI. We feel that there are tons of opportunities to be tackled. We are putting together an amazing team, and myself. I cannot lie, I have my professors around here. So, yeah. We have Juan Ocheniego, my partner, and lead AI engineer. Juan, please raise your hand there, that handsome guy there. One of our co-founders is Pablo Hoffman, the co-founder of Site and Scraping Hub and the creator of Scrappy. He's an amazing guy. That's me. And we have an advisor, which is a fellow of the university here also, PhD Nicolas Loeff, the director of engineering and ex-Google. So what's our approach? We are creating super fun and amazing prototypes, as well as we create business strategy for them. You know, there's a ton of opportunity with these large language models, but also lots of uncertainty. You may have heard of the hallucinations and that kind of stuff. So our approach is to create prototypes as well as we create business strategy that could make these prototypes grow fast. And remember, every company you admire, all the logos that you see here, were once an idea in someone's head, and often the wrong idea. So Twitter was a radio streaming service. Hugging Face, for example, Omar, correct me if I'm wrong, it was a chatbot for teenagers, and now they're changing the world, you know. So the point that I'm trying to say is that sometimes having the right idea is not the most important thing, but to getting started. What's our status? We are building amazing prototypes, we are growing as a team, and we are fundraising a few $1 million. So, could it be possible to create AI-first product companies that reach massive scale from Latin America? The answer is that we don't know, because no one has ever done it yet. But we do know that we will do our best to create them. We will put our efforts, our intelligence, our hearts to create them. If this message resonates with you, we want to know you. If you're crazy enough to pursue that 0.0001% of chance that this may happen, we want to know you, and we want to welcome you. Thank you very much. Feel free to drop us a line to welcome@brainlogic.ai. It's been a pleasure.
We have time for a couple of questions. Okay.
Well, hi. I didn't get why Sam Altman was in your slides.
Yeah. Hi, how's it going? Sorry?
So my question is why Sam Altman was in the slides.
That's a good question.
I didn't get that.
Okay.
So I think if you can clarify.
Yeah, of course. Yes. Why Sam Altman wasn't on our slides? Because it's a huge inspiration for us. And he states that now is the best time in 15 years to start a startup of an AI company. So that I was trying to validate why are we doing this right now, why it's important to start companies like this right now. Thanks for the question.
Any more questions?
Okay. Hi.
What you said really resonated with me.
Wonderful.
Because the only way, especially the bit about why don't we create those big companies here? And so I think the desire is there. I can see it from you.
Thanks so much. And you've been a great inspiration for us.
Thank you.
And a great T-shirt also.
That's from the last KHIPU.
I know.
So what's stopping? What are, because there's a lot of things you could do. Like, for example, you go a few miles away from here, 2 hours away by plane and so on. There's all this material that is used to make all those beautiful batteries for all the electric devices and so on that make people feel good about their impact on the environment and so on. And it's all being extracted from here, but none of that trickles to the people here. So how do we ensure that we can build a tech here or any other tech companies? Not just like language models and so on, but like even stuff like batteries and so on that stay and benefit most of Latin America?
Yeah, so that's a great question, and thank you very much. So we have many opportunities here in Latin America, as well as we have many challenges. For example, access to venture capital is not that easy here. So if you want to create batteries here in Latin America, you will need a ton of money. So there was, we were in talks with the government, and how we don't bring Tesla here, to create some batteries here. Actually, it isn't that bad idea because we have 95% of our energy matrix is renewable. So that's interesting. But the thing is that for us in Uruguay, we're a small country, but in Latin America, the access to VC capital is little restricted. It's not as the same as Silicon Valley. That's one of the things that we are trying to leverage now, because since we started 14 years ago, we created a I mean, it's not fair that I tell it, but an amazing company like Triolabs. We have one of spin-off that's called Monkeyland that was acquired. We have now the leverage to attract bigger capital opportunities. That's one of the reasons that we started this new journey to create, hopefully, a unicorn. There are things happening also. For example, last year, I don't know if anyone knows, but we had the first unicorn in the Uruguayan history. So dLocal, a payments company. So this gets more attraction to the ecosystem, more investment. So it's a super understandable question. We as entrepreneurs are trying to create more success stories so we can get more capital, because at the end of the day, no one will take care of Latin America as much as we do as people from here. So we can talk for a long time after the talk if you want, and thank you very much for the question.
Thank you very much for the talk. Please let's thank our speaker.
Thank you very much, guys.
All right, our next speaker is Pablo Florquín from the Universidad of Montevideo, UM. Pablo is an industrial engineering from UM and holds a PhD in physics from the Institute of Interdisciplinary Physics and Complex Systems of the University of the Balearic Islands in Spain. He has extensively worked in the field of AI at companies such as BBVA, Data and Analytics, and he is currently a CEO and co-founder of Trivium.ai and a professor at the University of Montevideo, which we'll be hearing more about.
Thank you.
Please.
Thank you for the presentation. Hi, everyone. Thank you to be here, just listening to the sponsor talks. Much thanks for the organizer for such a wonderful conference so far. I'm having a great time, learning a lot, or better, I'm removing a little bit of dust, because I was once a researcher and a data scientist. So what is this talk about? I'm going to talk about briefly Universidad de Montevideo, specifically about the data-driven programs. And in the second part of this presentation, I'm going to announce a new undergraduate program, okay? But which is the objective? So many of you are PhD students, postdocs, seasoned researchers. So of course, we don't want to increase our tuition, okay? That's not the objective of this talk. What we want to do is to be part of an extended community of research in Latin America, and to be part of that community and foster collaboration within universities, research centers, and companies. So with not further ado, let's start with the presentation. Universidad de Montevideo was founded in 1986. It's a private non-profit university. Right now, it has 5 schools: humanities, law, economics, communication, and engineering. It has also a business school, an MBA school, and 2 urban campuses. One is close to Estadio Centenario, and the other one is in front of LATU, Laboratorio Tecnológico del Uruguay. So some honor badge there. Is the first private university according to the QS ranking, and also is in the top 500 worldwide universities and the top 100 universities in LATAM. Also is a recognized teaching center of the University of London. So these are our data-driven programs. Okay, so the first 4 is postgraduate level programs in data. As you can see, business intelligence, data science, digital marketing, data science and big data. And the 5th one is a master in data science. Also in 2019, the university started undergraduate program in data science for business, okay? And what I'm going to present right now is a new undergraduate program that, if you tend to think, these six things, they are more based on the business side, or what we can call the front-end side of data. So, to start with why, okay, why we want to offer this new undergraduate program, okay? As you can see in the previous offer, and this is common for many universities in Uruguay, also in the region, most academic offer, it's business-oriented, okay, and mostly in data analytics, data science. So, when dealing with companies, with tech companies, there's a scarcity of technical backend roles in data that these many companies from traditional sector want to transform into a data-driven, data-savvy company. So they lack these backend roles in the data sector. This is another one of the reasons. And the demand for data-related technical roles is consistently increasing. 5 years ago, for instance, when I was working in a tech company, everyone was a data analyst, everyone was a data scientist or a BI engineering, but we lack roles in the data engineering and also machine learning engineers. And in 2017, Andrei Karpathy made a post about software 1.0 versus software 2.0, okay? So basically, I think that you all know this concept, but software 1.0, the classical stack is you have a set of requirements, you have a program, you have a black box, do computation, you get the results. Software 2.0, you get data, you get the results as inputs, and you obtain a program. And this changes everything from the logic of a programmer or for coding, okay? So we want to put these things into the new undergraduate program. So next is the how, okay? We have been dealing with the why, and the how is, again, as I said, we want to introduce these two roles in the industry sector that are data engineers and machine learning engineers. So these are back-end technical roles. And for what? Also to pursue this research and development in Uruguay and also in Latin America. And finally, as you can imagine, I've been saying all along in the presentation, is that we want to launch what is called Ingeniería de Datos e Inteligencia Artificial, that is a 5-year undergraduate degree. First 2 years are common with Ingeniería Informática, computer science, and we will starting this undergraduate program in 2024. So thank you, and as I said at the beginning, we want to foster collaboration within universities, research centers, and companies. You can write me here, and I'm glad to collaborate and foster this research among Latin.
We have time for one question. Okay, so if there's no more questions.
Thanks.
Javier. Right. Our next speaker is Javier Precoci from Sense. Javier received his PhD from La Universidad de la República in satellite image processing in 2016. He also holds 2 master degrees, one in computer vision and machine learning from INS Cachan, France, and one in computer science from Uruguay. He has been involved in image processing, computer vision, and machine learning projects since 2004, and now he's going to tell us a bit more about Sense in a second.
Okay, hello, good afternoon to everybody. I am Javier Preciosi. I am very, very glad to be here this afternoon. This is, as it was mentioned in the presentation, I did my degree here. My my master degree and my PhD. So I am extremely thankful to this university for what they gave me. They gave me. The objective of this presentation is just to explain a little or present a little of what we are doing at Digital Sense. And I want to start by mention how I end up on this company. Basically, as much I guess as some of you, I enjoy doing research. This is one of the reasons I did a PhD. But also as an engineer, I wanted to put some of that knowledge near the industry. And basically, the objective of Digital Sense is to combine both things in that way, doing research, doing businesses, doing projects with the industry, but also doing research. Right now, the company has 15 years. When we started with the company 15 years ago, we were basically a computer vision and image processing company. We are still doing much of our work in those industries, but obviously the field has changed a lot since then, and we try obviously to keep in track with all those new stuff. And right now we are more than 40 or nearly 40 people, and for that those 40 people, nearly 35 are professional staff, and we are glad to have in that team a very well-formed and focused team. We have more than 8. Well, we have 8 masters and 6 PhD, but also we are also forming some of the people which working on the company, and helping them on completing their master degree or PhD. The objective of, now I will present basically 2 works that we have done in the past years regarding, which are strongly focused to research. There are a lot of others that you are, and I invite you to go to the booth and see some other more industrial projects. But this presentation will be focused specifically on research. The first one is a remote sensing project. So Uruguay is an agricultural country. We have nearly 7% of the area of the country is devoted to agriculture. And in particular, soybean represents 14% of the total exports of the country. So it's very important to understand what is happening in the fields, what the agriculture producer, the farmers are producing. So the objective of the project was to understand that, to do a classification of what the farmers are doing in the field. For that, we have we have 2 data sets. One data set provided by the Ministry of Agriculture, which is a noisy one because it contains basically the declaration of what the farmer will be doing and not ground truth, I will say. But then we have a second data set, which is more curate in the sense that these are from 2 agricultural cooperatives, and it's supposed to be correct. The data set is also unbalanced because soybean is the majority of the crop here in Uruguay. So basically, the method is we use satellite images which are free. In particular, Sentinel-1 and Sentinel-2, they have a lot of good features for working for this specific problem. We create for those a time series and use that time series to build feature vectors to train a classifier. You can go to the publication to see the results of this work, which is a collaboration between our company, this university, and this institute in particular, and INIA, which is an agricultural institute in Uruguay. The second project that I will mention is anomalies and quality inspection. Here it starts from a client. The idea is to detect anomalies in the leather for the automobile industry. And in this way, so the way we model the problem is like a detection of an anomaly going out of what is considered the normal distribution of the data. That is because we have a lot of normal data and very few anomalies. This, basically the model or the pipeline was first a feature structure based on transformers, then a U-shaped normalizing flow net, which produced basically two outputs. One is a probability density map, and the second output is a threshold. It's a segmentation of where the anomaly or the defect occurs, which is based on a method, and a contrario method, which is an unsupervised method, which is very interesting. These are some of the results in objects, texture and anomaly free. And here are some of the articles that we publish based on this work. And in particular, what I present is pre-printed in archives, so you can take a look on that. This is, again, a collaborative work between Digital Sense and the University of Uruguay. And then I had a third one, but I think I ran out of time. I don't know how much time I have. One. Okay, I will skip this one. And this is also because I have to discuss this with Sarah, because there are a lot of things that she explained today related to biometrics, and in particular to bias, that I want to discuss further. In any case, there is a publication that you can take a look at if you are interested. It was a work, again, between this university, this Digital Sense, and a colleague from the Paris-Saclay University in France. Well, that's it. Thank you very much for your time, and I'm open for questions.
We have time for one question. Okay, so if there is no more questions, let's thank the speaker again.
Thank you.
And yeah, so we have now a break. The goal is to start the next session at 4, so please get some rest.
guy.
Hello, everyone. We are ready to continue. Please. Hello. Please take your seats. Okay. So it is a great pleasure to introduce our next speaker, Nando de Freitas, who will be talking today about large language vision models. I invite you all to read his full bio from the KHIPU website, as it is both an amazing and inspiring story, which I can only attempt to summarize here. Nando was born in Zimbabwe and was a refugee from the war in Mozambique. Because of this, he spent most of his childhood in Portugal and Venezuela. He then moved to South Africa, where he studied electrical engineering and a master in control at the University of Witwatersrand. After that, he obtained his PhD on Bayesian methods for neural networks at the University of Cambridge, and then did a postdoc on AI at the University of Berkeley. He became a professor at the University of British Columbia in 2001, and subsequently at the University of Oxford in UK in 2013. He joined DeepMind in 2017 as he joined DeepMind in 2017 as a full-time director of research to help with the vision of solving intelligence so that future generations can have a better life. He has won many awards, and is perhaps an understatement to say that he has done a lot to support and promote diversity and inclusion everywhere he goes. So Nando, let's please welcome our speaker. And Nando, the floor is yours.
Gracias, Tatiana. Muchísimas gracias a vos de estar todos aquí. Hace 2019 que no vengo. La última vez me dieron esta ramera. Aos brasileiros, bem-vindos ao KHIPU. Espero que gostem muito do que está passando aqui e de conhecer os nossos irmãos do resto da Latinoamérica. I'm going to give the talk in English, though, to try to make sure that everyone understands. And also, as it gets technical, I don't want to inflict you with my lack of technical language. Thanks to the organizers, thanks to the university. You've been amazing. You were amazing last time, and you're amazing now. I'm hoping I will collect more student signatures. I probably would have to wear this for the party at the end. And yeah, it's great to be here. It's so wonderful. I should warn you, I just basically landed. It was a very long trip. It got delayed, ended up not sleeping much. So at some point, I might either fall asleep or start telling you really wrong stuff. Stop me, ask questions. Please ask lots of questions just to make sure I stay awake through this. Mate. Oh, that stuff kills me. That's the one thing. Yeah, it's the one thing it's hard to get used to. All right, let's go into the talk. So I think there's going to be some overlap with the talk that you've already seen here on generative models. And maybe I'll just have a bit of a different perspective on this. And these are really important concepts. That's what the talk is all about, those three models. And if you know these three models, and you can distill them to the very basic, most simple things of what they really are, because these things are accessible to anyone. Doing AI, building chatbots like ChatGPT or language models and visions, those things are not hard to do. The know-how isn't hard, and we can simplify it and we can understand it. Of course, then there's the difficulties of having access to compute and data and so on. But even that, I guess I should say here, because sort of to localize, there's a lot of stuff. I mean, there are people here from Hugging Face, right? Where are you? hugging face people, they're gone to Punta del Este, or because here definitely, I've seen there's plenty. So there's a lot of these amazing startups, Anthropic and so on, who are putting a lot of models out there, checkpoints, data. Like if you want to build a lot of stuff these days, if you are opportunistic, and that's my biggest advice, is be opportunistic. Don't try to build a fancy thing. Just see what's out there. Make sure you understand what everyone's putting on GitHub of all these big companies. And then just use their stuff, build on their stuff. Don't try to reinvent things, just build on their stuff. As long as you have the sort of understanding, the basic understanding of the idea, and you can do PyTorch or well, here you're using JAX or JAX, and then you're fine. I love JAX. I have a JAX slide, so that's. All right, transformers. I'll try to go a bit quick because you might have seen some of this. So, the first sort of big transformers are, attention is really an older idea. And in fact, it was a master student in Eastern Europe that came up with it. And but what it sort of became very useful was at Google when they were trying to use the idea to do massive throughput through neural networks to do translation. So the idea basically is you have, if I point, will people be able to see this? Yes. But not in the video, or yes? Okay. If it's being recorded, oh yeah, because it's being recorded, like, I guess. Anyway, so there's two big neural networks in a transformer, an encoder and a decoder. And let's look at it through the angle of do a question answering. So you could have a question, ¿Cómo se dice love aquí in Buenos Aires? Más. Está tan cerca, solo un río. Anyway, we change words to tokens. Changing topic. And then basically these transformers are neural networks that just, once you map a word to a vector, and this is kind of a lookup table, it's easy to do, they produce an output that's basically the same dimensions as the input. So if you put in 5 vectors in of 4 dimensions, then out you get 5 vectors of 4 dimensions. These will become available to a decoder that starts with a token that is usually just a beginning of sentence or token. And then the decoder produces, the first output word, like set as the first prediction. And then it does something that gives the name to these models, so autoregressive generation. So the SERP goes down to the bottom. It gets fed as an input to that decoder. Then it says dice, and so on. Now let's look into detail at what one of these models actually looks like. So here you can see there's the encoder and the decoder, and I would like to go through the details of what these models are doing. Because I think once you understand the very basic idea, then you can go and play with it and change the code and so on. So the first thing we do is tokenization. And what tokenization, you basically just go to find the sentence piece tokenizer. That's what everyone uses. If you're adding special symbols and so on, you have to do a bit of thinking about how to tokenize. Tokenization is actually really important. Like a big percentage of how performance depends on having a good tokenizer. It looks like it's a simple idea, but it's actually important. And essentially what it does is it breaks sentences into things that are neither words, but they're sort of like pieces of words or words with a space and so on. Those words then get fed into, so you first break them into words, then each of these things will become an integer. So, and these integers range over your vocabulary. And then for each integer, then we use a lookup table to map each integer to a vector. And those vectors is what I was referring as those tokens. Okay, so this, usually you call a pre-existing tokenizer like sentence piece, and then this bit will be part of the transformer training that will come up with the numbers that go in this vector. This is pretty standard stuff. Now, attention. How does attention work? I'm going to first discuss cross-attention. And it's cross because it'll be this network attending to the output of this other network. And let's say that the output of the other network is this matrix M, and this, the input to the attention module from this network is, I'm going to call it X. X also gets passed to another module, which we will go into later. So basically, the input of this module, if we look, if we zoom in, is a matrix that has, assuming that there's, say, 3 words, where are you, 3 tokens, then they get represented as vectors. In Uruguay, it gets represented as 2 vectors. And then multi-head attention will then generate 2 vectors as an output. And for the rest, I'm going to go into how that is done. Please do stop me, or if this becomes too obvious, just like shout for me to hurry up as well. For those who've watched my lectures and so on online, I do like to simplify things because I don't think no idea is hard. It's just about making it easy. And so let's look at this example again, where let's assume that there were 3 words here as an input. The words were, where are you? And so we have 3 vectors out here. I don't know what those vectors are, but let's just assume we have them. And assume that we have 2 vectors here, because here as the output I had in Uruguay. So I'm going to use D to be the model, what people call the model dimension, which is, say, the number of numbers that each vector has. And in this case, M has 3 vectors, and X has 2 vectors, indexed by M and N. The first thing that attention does is you come up with some linear weights. So this is just a matrix of parameters that we will learn by backpropagation. And all these matrices do is project the input. So the X will be projected into something that people refer to as the query. And then the M will be projected through 2 different matrices to what is referred to keys and values. So it's inspired by sort of these key value databases. You have a query. The query allows you to find similarity to keys, and then you read the values corresponding to where the keys indicate you should look. After we project them, we will compute the similarity score between Q, the query, and the keys. So dot product multiplying, so we're essentially dot producting these vectors, and you end up with something that is of size n by m, which is basically the similarity of each vector, each orange vector to each blue vector. And after you do that, we do some normalization, which this matrix basically has, real entries. If we normalize with this thing called softmax, which is basically where you exponentiate every entry of the matrix per row, and then divide by the sum. So you just make sure that you get a matrix so that each row sums to 1. They can be thought as probabilities. And lastly, you then use that n by m matrix of weights to multiply this vector v, which is m by k. So basically what you're doing is you're indexing into the m entries. If the weight was, for example, 1, 0, 0, and the dimensionality here of v was, v had 3 elements, element 1, element 2, element 3, then basically only element 1 gets selected. Okay, so this is basically, you can think of this as a selection mechanism, pulling the information that is needed. And finally, we do one more linear transformation, and this is just so that the output is again on the same dimension as the input. This is it. This is all of attention in the one slide. Now, there is something called self-attention as well. And what self-attention is just there's no M. It's just X. So the X gets split into three things. So the X will be used for the query, for the keys, and for the value. That's it. That's all self-attention is. You find a similarity. There's going to be something else here. I will explain it soon. We find again the weights, and once again we read, and so on. So what are these weights? We're trying to build a language model that predicts the next word based on previous words. And so we don't want the prediction, if we try to feed in all the words here, a big vector over the whole sentence, the whole answer, and we're trying to predict, say, the first word, then the first word should not look at the second word and the third word, because otherwise it's just cheating if it's using the future words to predict. So we somehow need to blank it. And this is going to be done with a mask. So for example, suppose that I was, the sentence, the output sentence was, I am fine. Then in order to make a prediction about the word am should not look at the word fine. So when you multiply, so this guy should be 0. You shouldn't be reading the information about the word fine to predict something about the word am. So you shouldn't use the future to predict the past. So we want to make sure that this is causal. And in fact, this is sort of called a causal mask. And so the way it's done is people simply add a matrix. This is the mask. So these are the logits, what people call logits. Sometimes they're called scores as well. And you just put a minus infinity there and zeros. So the minus infinity, because we're going to take e to the minus infinity, so we want to get rid of those entries. And when you add them, then you get something like this. So basically, it nukes all the stuff on the upper triangular. And then when you do the softmax of it, it basically renormalizes the entries so that it still sums to 1. Okay, so the weights still sum to 1 per row. But they're 0 for the words in the future. So you don't look at the words that are in the future. Now, why do people do masking? Why is this a useful trick? Yeah, thank you. Parallelization. When I showed you that picture in the beginning, where you have some words and you predict one word, you predict the next word and the next word and the next word, I'm going there one by one, autoregressively. And at inference time, when we deploy the models, that's what happens. But that process is very slow, because imagine, every time you put in a new word to predict the next word, you need to feed this whole thing through a network. And if this thing has billions of parameters, it's just, yeah, you couldn't serve this. To make, I mean, you couldn't train it efficiently. So at training time, you put in the mask so you can feed in all the words at the same time and generate all the predictions at the same time. So you're not just predicting which words come after the first word, but you're also jointly predicting which words come after the second and after the third and after the fourth and so on. So you're making all the predictions in one go during training. And the mask is a really clever way to achieve that. It's actually one of the coolest sort of tricks, and it appears everywhere. Like Pixel CNN, which was one of the places where this was first heavily used, I think that was the brilliancy of it. Another thing that appears is this question of heads. So we're saying it's multi-head. So the explanation I gave so far is assuming that there's only one head. So what are heads? The idea of heads is illustrated with this picture. You have the queries, the keys, and the values. They're all vectors. And so what you do is, allowing the model dimension, you just break them. Like in this case, they're being broken in half. So we just make smaller vectors. And then the assumption there is that these vectors are independent of each other, basically. So we're now going to send each vector through a transformer. Okay? And then at the end, and so we compute the output of each of these heads. So this is now multiple transformers going in parallel. And then to make them correlated again, we multiply times this output parameter. And so the idea here, I mean, there's many reasons why you would want to do this. You could think of each head will represent a different aspect of the input, different aspect about the sentence. But also, just from a very pragmatic computational perspective, by breaking these vectors into smaller vectors, you end up doing operations that cost less, either in terms of storage or in terms of computation and so on. And then you regroup everything by using this final operation where you append all of them together, you concatenate them and multiply them by a vector W. So essentially you should think of this in a way, this is a linear combination of basis functions. Each head is a basis function. It's basically the neural net, fundamental neural net idea, and you're combining them to create something that's very expressive. So it's a very clever trick. And it's a useful trick to know because it actually, there are models that are trying to do better than transformers because transformers actually really suck in terms of the context length and to how long this sentence can be. They're also not very good at doing fast inference and so on. And so there's all these new families of models like S4, H3, and actually every time I look at Twitter, there's a new one. But often they use tricks like this. So it's useful to see these. Once you know the few tricks, you can sort of apply them over and over again. This is the code for it. And I highly recommend this paper by Noam Shazir. I think it's one right head is all you need. This is actually with multiple right heads. But the code looks just like those equations I went over with you guys. So except that here, we're going to add dimensions because usually when you want to train this massively in parallel, you have sequences of certain length, but instead of just using one sequence, you also want to use multiple sequences. So you want to use what people call a batch. So to do batch processing. And so now X has an extra dimension, which is a batch. So in other words, you have B sequences of length D, which get tokenized into vectors of height D. And that's M. And you also have a mask. These are the matrices of parameters that we went over. And so it's exactly, using einsum, this is actually code. This is not, it looks like a comment, but it's actually code. It's actually specifying what the dimension should be. You can use einsum to then multiply x times pq and m times pq and m times pv, and this line of code just makes sure that you have the right dimensions. And this is how you introduce heads. You just basically created this new dimension heads, thanks to having done that to having specified that in these matrices of parameters. And we get the keys, the queries, the values. We compute the logits, which is q times q. We compute the weights by the soft mask. We add by the soft mask, then we add the mask. We compute O, Y, return Y. That's the code. The code looks exactly like the expression we went over. Questions?
Why do you need to send the mask as a parameter? Isn't just the upper diagonal of your...
Because you may want to do other things with a mask, not just to mask. So trying not to predict the next thing is a very common type of mask, but you may want to play other games with masks. And I actually will bring some examples of that later. Good question. Okay, let's move on. Actually, I've been looking around for a clock so I can keep track of time. 4:30? Oh, thank you. And I have until 5? South America. It's a terrible joke. 5. All right, so I'll go over these models, and I'm going to wow with videos and so on of all these things. Once we understand them, we can use them. There's a feed-forward layer, which is just kind of like an MLP type layer. And this essentially, actually, Lucas Bayer has a beautiful set of slides, and I'm reusing some of his here. The feed-forward, essentially, you think of as an MLP with a JELU basis function, which is basically, it's like a ReLU, but it's continuous. If you just Google it, you'll find the exact shape on Wikipedia. And the key thing here is that you actually make it bigger, do the nonlinearity, and then go again smaller with this perceptron. And often, well, at least in the Haiku code that I will point you to, it's a factor of 4 bigger. So there's a lot of the parameters of the model are actually in the feed-forward layers. Add and normalize is also very common type of, and this basically, each of these things is a Haiku module. Okay, and once you have Haiku modules, you can also create another Haiku module, which is the transformer Haiku module, and then you just use that module to do your language model. So the language model is actually just about 10 lines of code once you have the Haiku module and you have your data loaders and so on, and evaluators. Add norm, essentially, it does this sort of operation. The module, could be any module, like, for example, the multi-head attention. The way it was done in this paper, which is they would take the input, pass it through the attention module, and then they add that to the input again. And having these skip connections, this is what the ResNets did very well. This allows for more efficient training. So information can propagate much more easily through the branches. Then it's normalized. And here they use layer norm, which is if you, for example, for a single layer, you look at all the activations, and then you just make sure you divide by, you sort of subtract the mean, divide by the variance. So you, regardless of how you do normalization, there's many ways you can do this. There's RMS normalization. So what you want is you don't want some inputs to be very big, some of things to be very big and some things to be very small, because then they're not, some will dominate the others. And you'll have all sorts of bias, as well as your training could become unstable and will explode. So normalizing things so that every sort of features between 0, 1 is a good idea. More modernly, I will show you the actual code that's in GitHub for the Haiku transformer example. It uses more this sort of modern approach where you first normalize as you go in, you then apply the module, and then you add. We'll see that later. And the output layer is just basically something that takes you to the space of probability. So you basically, we had a vocabulary, those integers, and then you just get a probability over all those integers to sample from. And how you sample, whether you do greedy or whether you do over, like a beam search over several time steps, there's all sorts of ideas, typical sampling, nuclear sampling, and so on, different ways in which people do this. I don't think they, in my experience, make a huge difference. But okay, so, but maybe it's just a question that we're needing more research there. Let's look at 3 possible things we could do this, because once you have the Haiku modules, you can basically combine in whichever way you want. One way to do it is encoder-decoder. That's what we've been doing. These are the D5 family of models. There you can find them on GitHub. Alpha code, which I will just mention briefly, was also like this, where the input was a description of in natural language of what you want the machine to do, and then the output was code. So it's just basically having machines that can read a problem specification, generate the code to address. So this is usually nice because you can sort of usually make this sort of like short and fat so that you can have a long memory of, say, the description. And this one can be tall and skinny, so that it does many sort of thinking steps. And they are, so I'm saying thinking steps, at least algorithmic steps. Because a neural network is just a way of expressing an algorithm. Any algorithm can be written as a neural network, vice versa. You could extract it, except with neural networks, you learn the algorithm. That's the most powerful thing that's happened is that we realize that any algorithm that we use, we can learn the algorithm as opposed to we humans trying to do it by hand. So that's why you should always trust the network, let the network learn. Another architecture that's very popular is BERT. So in BERT, what you do is you have an input sentence, and now you apply a different type of masking. So this is sort of input masking, where you actually mask some words, and then you try to predict what were the words that were masked based on the context. And this is sort of the big language hypothesis. A lot of, a word often is, what a word means is based on the context with the other words that appear with that word. And this is very useful for images, as we'll soon see. And more recently, I think the buzz is more in not using encoder-decoder architectures, but just using a single decoder type architecture, like this one for language modeling, where there's a start token and then the cat, sat, predicts sat. And this one is the one that's in the KHIPU GitHub website. But it's also, the sort of architecture is what's used in, say, GPT-3 and a lot of language models, Chinchilla and so on. So again, the same idea here. You start with embeddings. You add, I didn't mention, the position encoder is just basically a smart way of saying where does the word appear? Because attention does not keep order. It's invariant to that. And so you have to add to each token an extra bit that says the location of the word, so you know where things are happening. Once you have that vector and you feed it in, the first thing you do is to sort of lay a normalization. And that's exactly what you're doing in the code. So the first thing you do is lay a normalization. This is actually the call method. Then you do multi-head attention. So here you define multi-head attention, and then you apply it. This particular code was using dropout, which is a regularization technique. It's a given layer. I won't have time to cover it, but it's just think of it as regularization. Then you add everything. The residual connection is here. And of course, then you propagate it. So there's always a path to the input throughout the net. And so on. You can follow the rest of the steps. But yeah, the code really looks like the thing that you implement. It's sort of very clean, very easy to do. Also, as you see, we've kind of put modules here that are slightly different than the previous thing that everyone finds on the typical picture that we have. And when you're playing with these models, you should be prepared to get rid of some of these modules or to add new modules. That sort of plug and play is what allows you to sort of do sweeps and find out how well different models do. I mentioned this one. Let's look now at examples. AlphaCode was a good example where you feed in as the input like a problem description, and then the output was code. And the models work quite well these days. So it's pre-trained on GitHub, and then it's fine-tuned on a few thousand coding competitions. If the models are large, one of the sort of amazing things, and this is important actually, they're big models. They're very heavy to pre-train. Most of us are not going to be doing this, the pre-training. But if you want to fine-tune it, one of the sort of remarkable sort of findings over the last few years is you need very few data to fine-tune them. A few thousand examples, and you can do all sorts of amazing things. Like with a few examples of code contest, then we could sort of have something that was actually quite competitive as a coder. Of course, the most sort of sexy, I guess, thing right now with language models are these chatbots. We've seen quite a few examples of these. And once you have a language model, this is how you build. One simple way to build a chatbot is you start by writing something. This is what people call the prompt. So this is basically input text that I wrote. And then, first I asked this chatbot to be nice. That's wishful thinking. And then asked, where are you being deployed? I'm currently deployed in Montevideo, Uruguay. Is that where KHIPU is? Yes. So I wrote all this. And then the model predicts. And it's just, this is language modeling. There's no intelligence here, just predicting the next character of what should follow. But because there's lots of dialogues like this on the web, it sort of has learned that texture. I mean, these models are kind of like texture models, like in all computer vision. And so so it sort of knows that it's a conversation between a user and a chatbot. I mean, it doesn't know that, but that's the right texture. It's just a conversation between a user and a chatbot. So it continues. And then it says things like, the best thing about KHIPU so far is the opportunity to meet people from all over the world. And that sounds like a great thing to say. And people love them because they say things like this. They also say other stuff. Here's another example. I can't decide because I have not seen everything yet. And this is also plausible. So you can draw many samples because remember, the output layer is the sort of softmax, it's stochastic. You can keep drawing samples. And so you have all these possibilities of what the model could say. And then as it would be nice if we could control these machines. They're amazing priors for language, but how can we make them useful? ChatGPT is one example for people working toward this end. I think they still have a lot to do, but they do something very simple, which is they collect actually human dialogues and then they fine-tune on those dialogues. Okay? If you want to do this, you can do it because there's lots of websites that have published the data for human dialogues, Anthropic and so on GitHub. You can go there with your language model, you can fine-tune it on that data, and then you can make your own chatbot. It's very easy how to fine-tune it. There's also a lot of work that people put into making sure that these models are safe, making sure they don't, deal with, I guess, trying to get some control in them, make sure they don't lie and so on. And it's incredibly hard to do that. And I think the hardest thing with them, is, which was alluded to in one of the questions earlier, is because a lot of stuff is contextual. There is a context where it's sometimes fine for me to say something, but there's a context where it's not fine for me to say that. I might say something if I am talking to adults, and I wouldn't say that if I was talking to a 5-year-old. And so context really matters. And right now the language model is an interface between the web and a universal user. I guess in the future we'll see a lot more personalization. And also the interface shouldn't be about the web. You should be able to use the chatbot as a way to interact, and a few companies are doing this already, interact with a book or interact with a movie. Just narrow the information set so you interact only with a specific information set. Interact only with papers about transformers so you can have an intelligent conversation about transformers as opposed to it being about the whole web, because every time you bring the whole web, things sort of go very diffuse. Question?
I have a question about that, because sometimes you ask questions and the ChatGPT replies with facts or pseudo facts, but it doesn't tell you, like the level of certainty it has on these facts, and sometimes they are not real, right? So it's kind of
you should never trust the chatbot. So there's a lot of great work. So let me show you some of the stuff in that direction that people are trying to do. So one is through tool use. And we saw already a few examples before when we talked about retrieval. So I can also sort of start priming this to do search. So basically, what is Montevideo? Then I add a third user, which is search. You could add also a third user that is someone watching the conversation. So you get this sort of awareness sort of view. Or you could add a third person, you try to get, there's all sorts of things you could do. This is basically a model that writes a lot of things, and people do this sort of chain of thought idea, which is the model says, let me think step by step. You put this prompt there, and then the model generates a bunch of blurb. And remember, when the model generates, it also takes it as input. So you should think of all these tricks as what the model is doing is it's writing, and then it's reading what it's writing. It's using the external world. It's using tools. Humans, most of our intelligence is not in our heads. It's in the people that surround us. And the information, because you basically rely on people to ask questions, to get things done. You rely on books to get information. You rely on computers and so on. So a lot of our minds are external. And so just like for us, that's been very useful. We know when to use calculators with calendars, email, partners, friends, colleagues at work, and so on. Then models should also start using a bit more of that to become much more effective as opposed to just relying on their own single brains. And so here the tool, if you start teaching models to sort of search before they do the answer, then they start sort of doing something much better. Of course, the thing that I did this at night, late at night on the plane, so they're not the best examples. I mean, you might, it's amazing that it works. Actually, this website does exist in this case, I checked. But you should also, what you should do is then you should launch this as you should put this on the browser, and then you should read which information comes back, and you should try to parse that information. So something that also maybe brings the information that's in Wikipedia, and then you do the answer. So people are trying to do things like that, tool use. I think tool use is going to be much bigger. But again, the way I like to think about these chatbots, like they're interactive. Language is a very powerful thing. We interact with language. So if you think about teachers, there is no reason why a teacher is needed. A teacher is just an interface, an interactive language interface, because you could just get the books and read the books, and the books usually are better than they have more content and so on. But MOOCs fail, basically, because students don't want to go and read a book. At one point, and by failed, I mean there was a point when MOOCs came out, like Coursera and so on. The talk in town in every university is, we're over. We're going to be displaced. Teachers will be displaced. But it didn't happen, and it's because students don't want to go and just read the damn book. They want to interact with someone, and they want to sort of quickly get the information that's relevant to them, very personalized. They sort of have some intentionality of what they know, where they need information, where they don't. So it comes back to this question of uncertainty and so on. And the teacher, believe it or not, actually understands the students. I mean, good teachers do. They know their level. They try to have the material at their level. And all that, and so the language model then is very powerful because it provides that interface. But for that to work well, it has to know well the material. It has to understand that it's teaching calculus, so it shouldn't just be talking about, I don't know, Ariana Grande's shows. In the context of calculus, or maybe it's just to motivate. And then it has to understand who it is talking to. I think there's lots of opportunities. You know, we're talking about startups and so on. Just being able to do personalization with these models, there's a lot of opportunity there. And so personalization at both ends of the interface with the content and with the user. Lawyers, who needs a lawyer? You have all the legal documents, you just read the legal documents, and then you make the best decision. The problem is you don't have time to sort of learn all the constitution laws and technicalities and read the 500-page contract to build a new building. You just don't have that time. So you then rely on a lawyer who sort of understands you, and you ask the important questions. Will I go bankrupt? Are you sure? And the lawyer reassures you, and you take that big leap of faith. So for language generation, these models are incredibly useful. And it's just a very simple idea that we could just go and play with the code today. But they're also useful when you start combining them with images. So we get into vision. Because like in this example, I love this example from ChatGPT, where someone asked it to sort of come up with interior decorating ideas. It generates a text, and then that person took these proposal ideas and fed it to, I don't know, DALL-E or Midjourney or something like that, and then generated the rooms. So it's amazing. It's like a really cool, creative tool. I don't know if we're at the point of full-blown creativity where the line is, but one of the most remarkable things that has happened over the last year is that we've thought creativity was going to be the last thing that gets solved in AI, and we're seeing that the models are actually doing a lot of very creative stuff. And I think combining the models with people will be amazing. We're coming to images. So how do we build? If you want to do image classification, for example, with a transformer, one simple idea, which is what people call VIT, is you break it into boxes, and then you do these you feed these patches with linear projections. You add this position encoding, which says where it's happening, the sequence. And then you do a transformer. So again, a transformer could very easily be used for images. You just basically have a different tokenizer. You have a tokenizer for images. Thank you. Another good example is of the same ideas where so if you want to go from images and text to text, and again, you could use pre-trained vision encoders. You could use pre-trained language models, and then you just learn adapter layers that allow you to sort of go from images and text to text. And if you do that, you can build sort of cool things like this. You can present images with text, and then in few shot, the model answers queries. Like there's a very clear example here, 2 + 1, and then the model outputs this. Then you show this image with this. And if you show this image, then the model outputs this. Or you can do something that's become very popular. You can put an image, you can do dialogue now with images. You can insert dialogue. By the way, dialogues have become quite important. Dialogues can be very multimodal. You can insert anything you want there and talk about that sort of thing, provided you can tokenize it. And there's another example. We covered transformers. There were 3 models. So these ones, I'm going to go faster. VQVAE, highly recommend you go read a paper. What it does is essentially, it goes from an image through, I don't know, CovNets and so on. And then at the output, when you have these responses, these activations, you basically search in a database which we basically create code books. So the idea is you try to discretize this into just a finite set of vectors. For each entry, you find the closest one, and then you just basically record which ones are closer. And then you pull the vectors out of here corresponding to those positions, you insert them, and you decode. Because essentially what you're trying to do out of this model is, well, you're trying to do good reconstruction, but also you're trying to get a good code that represents images. So you're learning a tokenizer. Once you have a visual tokenizer, you can now use the tokens. This is just basically a tokenizer through one of these VQVAEs or VQGANs. Sometimes there's an extra loss to get more sharpness. And then again, it's the same. You could use any transformer that we have. So like there's this model parti, which generates pretty cool images as you make the transformer bigger and so on. And it's just essentially a language model. It's the same technology. It's just a different tokenizer. Here is a different. The problem with those models is that now the tokens go over the image. And so they're very slow. So this is how long it takes to generate an image. And if you use something like BERT, a different type of masking, it's much more efficient. So MaskGit, every idea out there always uses the same building blocks. You have a VQGAN encoder. You can pre-train it. Once you pre-train it, now you use this sort of masked unmasking, which is basically BERT type thing, where you learn Just start with a few pixels, most of stuff is missing, and then you try to generate the whole thing. And so the usual decoding was going like this, and part-time, with these type of models, you're unmasking the image as you go. And I think you saw a bit of Fenaki, and I'm looking forward to meeting the author of this paper here. And it's an amazing, amazing model. I love this model. You've seen it, so I will skip. VKVAs, important building block. Next building block that's very important, diffusion. Sometimes they present diffusion like this. You have an initial image, you put it through a diffusion, you get noise at the end, and then we know that we can invert these differential equations, so we can then write the backward process. We can estimate the only thing that has parameters, which is this thing called the score, the derivative of the log of the distribution with respect to the input. And if you can estimate this, we can actually reconstruct the image. So you can start with noise and generate images. Here is diffusion as a network, and pretty much everything you need to know. We're going to go from the input, and we're just going to keep adding noise. This is the network. The network has many layers. This layer is just adding noise. This layer gets repeated. There's only two modules here. One is add noise, and another module will be undo the noise. And the undo the noise usually is a UNet, which is just a network with extra skip connections. You can think of it like that. It could be many different types of architectures. And so what we do here is we basically take the input, we add some noise, Z, it's just Gaussian noise, and we still preserve the input. So the image gets blurred more and more and more as we're adding noise. And one thing we know about adding Gaussian noise is that it's geometric. It exponentially becomes noise. If you want to think of what that means, remember COVID? When people are talking about exponentials, it's basically someone gets it, and all of a sudden, boom, everyone has it. It's sharp image, and then very quickly, everything is noise. So after a few steps, you get noise. And actually, you don't need that many steps. In the old days, people were saying, oh, we use the continuous math. Actually, you only need discrete time math, because these days, I think with very big models, even like 10 steps does the job. So there's no need for all. Mind, the continuous stuff is still very important to design new algorithms and so on. There's some applications where that's really important. But you can either go and focus on the theory, or you can sort of focus on, say, if you just, as a practitioner, want to use these models. Now, to the noise, the blue things, I just applied the reverse equation. The way this equation was derived, actually, it's my friend Arnold who said that derived it in a tutorial that he gave recently at our group, is just using Bayes' rule. So you don't need to know all the French. If you know Bayes' rule, you can come up with this. I would be happy to go over this with anyone who is interested while I'm here. But essentially, it's an equation that basically allows you to undo the effect of adding noise to reconstruct the image. And the only unknown there is this thing called the score, which gets approximated by a neural network. And the score of the model is matched to the score of the data. The score of the data, because it's just adding noise, is analytical. So when you do, you get a very simple expression in the end for your optimization objective. And then you basically repeat the same equation over and over. It's an amazing model where through math we were able to come up with a very clever architecture. I don't think anyone would sort of sit down and just think of adding a bunch of modules that were just adding noise, and then just add a bunch of modules that were trying to undo the noise to get this. This can be trained in parallel, these guys, so there's no issue of backpropagation through time or the vanishing gradients or anything, because you basically trained each of these. It's the same module except with different data, so you train them in parallel. I'm going to skip this. This is a technicality. Stable diffusion, everyone's using it to generate images. Again, they use a pre-trained VQVAE, epsilon, these are the encoder, decoder, they're pre-trained. They use them to go to a dimension that is smaller than the data, so everyone can do this on their laptops, provided you have, like, I guess, a GPU in it. You add noise, and then you undo the noise. And to undo the noise, their module that they use is this UNet, which has this sort of extra skip connections. And then they also condition this on information. And that information could be text, so that you can, for example, draw an image of a cat on the beach. And it uses the same cross-attention that we went over in detail. So once you know those sort of basic ideas, the VQVAE, the cross-attention, you understand what diffusion is doing, you can understand this model. People use this to do images like this, but you could also take sounds, music. You could write a spectrogram. I don't know if this is going to work, but you can write a spectrogram of a song, and then it's just an image, and you just use the same code, and you can generate music. Oops. You can generate videos. It will be within the next few years that we'll start seeing Academy Awards going for best whatever computer generated. In fact, it's quite likely that music produced by humans will be a specific genre within the larger community of music. Music is very entrepreneurial. That's one field that's very entrepreneurial, because if you're not with the beat of what the young generation want, then you become outdated. So I think in terms of, looking how musicians work for startups is actually quite brilliant. And of course, just wanted to lastly mention that you could also, GAT was a project I was involved with, which is to basically shows that if you can tokenize things, you can actually tokenize actions as well. You can tokenize images and so on. So you can actually build a universal agent. And if you train it with all the data at the same time, you can build an agent that can learn to talk to you. So it can act as a chatbot. It can sort of label images. It can write poetry. It can code. It can control a robot arm. So you start getting embodiment. It can control avatars in games and so on. I've always been interested how, we humans, it's just one brain, we can do all these things. So how do we it's just as a curiosity, how do we do this? And a big question that's never been demonstrated convincingly is, will that sort of extra embodiment that we get help with being able to talk about certain topics? There's again the question of context and grounding in order to be able to actually present the right ideas in an interface. I'm not going to go into this, but basically once you have tokens, you just basically use any language model to build a model like this. The difficulty in this is that, like, to run, say, 600 environments at the same time, it's a massive engineering undertaking. It took 2 years to build that with some very good engineers. So, but yeah, data engineering is very important. So the idea is also, why is this important? I want to learn a model that no matter what robot you throw at it, it will be able to control it. And that's essential because unlike other areas, whenever you involve the real world and there's hardware, one thing is sure, the hardware will evolve. What's available next week or will change. And so your model has to be invariant in a way to the type of hardware that you have. It's the only way you can actually advance research in, say, automation without compromising. And that's it. I think I have time for a couple of questions.
Thank you very much, Nando, for the fantastic talk. I'm sure you sparked a lot of ideas and questions to the audience, so let's start with
Thank you, Nando. So coming back to language models, so I was wondering why they are so fragile to jailbreaking, you know, like adversarial prompting, and because they are trained to play nicely, but you easily can jailbreak them, okay? And that has important consequence for all the startups that they are building on pre-trained models, okay? Imagine that you want to use a conversational chatbot for call center users, and then the users can jailbreak it to do whatever the chatbot wants. So that is not safe technology so far. So what is the reason for jailbreaking and how you can solve it if you are a startup that you want to use these pre-trained models?
I wish I knew. That's the billion-dollar startup. I'm not kidding you. If you can solve that, it's $1 billion. Not a million, billion. That's the biggest problem. How do you make this technology safe and accurate and so on? If we can control it, it's very hard to control. And you know, things like RLHF and so on, they're like sort of take you a little bit in that direction, but they're not enough. I think part of the fact, because these models, again, is this thing of context, it's about them being able to adapt continuously, you know, not just like freezing the model and then just kind of deploying it. And then there's this sort of trade-off. We talked about catastrophic forgetting, but the opposite is like being able to adapt as well to new information. It's very challenging. One thing I know is that it's very easy to make them do the right thing. It was very easy, as you saw, just a very short prompt, and you get this model to actually follow the right texture. So if you can do that to do good things, you can do it to do bad things. That's very clear. And we would be responsible to say that these models cannot be misused. But there's a lot of people doing research in this. It's one of the hottest areas. And you know, it's a wonderful place to be now, because actually there's a lot of opportunity to come up with some creative solutions.
Any more questions? Oh, there's someone over there.
Hi, Nando. Thank you for the presentation. So recently, Google published a paper on Palm E, which is like a Gato, but much bigger. And one thing that was interesting was that instead of using a lot of tasks, they just scaled up things. So do you think that multitasks for vision language training and deployment in robotics is necessary, or just scaling up things is going to be the way forward now?
It's a bit technical, but let me address it nonetheless, because it has an important thing in it. So what this paper does is sort of has, that paper is actually more like the Flamingo. It's actually an earlier version of Flamingo called Frozen. It's very similar to that model, which is basically you use the language model, you put in encoders for vision, and then if you already use the block, as much as possible, use pre-trained models. Don't try to learn them all. And so you can backpropagate through a pre-trained model and then just learn the vision module. And so these models can take images and text. It's like in a conversation, and then they can spit out text. So it's more like a chinchilla type model. And then they've applied it to robotics, where the assumption is that you already have lower level policies that, given a voice command, the policy knows what actions to actually execute. And it's really nice. It's really nice to sort of think of this hierarchically and do that. It's not enough, though. It's the real problem that we did not try to sidestep in Gato is that low-level control. Think about self-driving cars. It's easy for me just to tell the car, take me safely to my hotel in Punta del Este or something like that. Good luck. Because the real problem is not telling the car what to do. The real problem is the car interpreting that and understanding the visual scene and knowing which actions to take according to the visual scene.
Thank you.
And a car is a robot, so it's the most easily deployable robot at present.
We have time for one more question. Oh, okay, sorry.
Oh, there's 2 microphones.
Go ahead.
Me? So.
Oh, sorry. Hi.
Hello. So I think something that would be useful for these models to be able to do is to attribute their decision to some set, one or more training samples. Like, where did you get your answer from originally? Like, if you're doing asking something that is actually factual, it should have taken the answer from some website or one or more. And I want to know what those websites are so that I can make the decision whether to trust it or not, or go there and read the full thing. Is that something that seems technically possible?
Can I ask you that question? Because you know more about it than me.
No, not really, actually. I have no idea. I mean, it feels like something you can do afterwards, right? You go and look for similarities in your training data, but that doesn't, it's crazy because you have lots of samples in training.
Yeah, attribution would be amazing because when they, and then sort of, and also knowing when I was going to use, can I say that, bullshitting when you're not.
Right, yeah. Or if it's a visual thing, you want to know whether you're stealing content from some author, like a painter, and you want to know if you need to pay that painter for, I don't know if that's legally meaningful, but.
Yeah, because the problem right now with these models is you can ask, you know, I mean, you can try it with your favorite chat agent. Ask your favorite chat agent to tell you about this amazing movie that happens in Montevideo with teenage coders trying to win the Booker Prize. It will make up a beautiful movie about it, and that will make you want to watch it, and most likely that movie doesn't exist. But if, and maybe that movie actually exists, but then it should be able to look at the information about that movie, maybe the Wikipedia website, and be able to attribute that in its response. That would be an amazing thing to do. Hopefully, that's a great project for all the students here.
All right. Unfortunately, we're out of time, but Nando will be around. I'm sure he'll be happy to answer more questions offline.
Thank you.
Please, let's thank our speaker again.
Yo te presento. Go ahead.
So we are done now. We are starting the sponsors session, the last half an hour of the day. I'm very happy to introduce you to Paula. She is the only woman talking from the sponsors. So for the next KHIPU, please be aware of that, of the sponsors. It would be nice to have more girls of the industry talking here. So thank you, Paula. And Paula will be also a panelist tomorrow, so if you want to know about her path in the Women in AI event, so she will be there. So Paula is like, we are counting on you, for the girls are counting on you. But getting more seriously, no, it was serious, as I said before, but she's an electrical engineer from here, from Universidad de la República. She holds a master in technological business management. She was selected as a Google developer expert in machine learning and co-organizes machine learning meetups. She has also completed programs at MIT and Berkeley, among others. And she co-founded Marvik, who she will be talking about in a few minutes. Y agarra la vincha. Ya. No, la vincha. Acá. Acostúmbrate.
Hola.
So, please welcome Paula.
Okay. Well, hello everyone. It's a pleasure to be here. I wanted to say thanks to organizers to putting up together such a great event for the Latin American AI community. So first, I wanted to start by introducing our company, Marvik. We are a machine learning consulting firm. We deliver end-to-end solutions, state-of-the-art AI solutions. And actually, this picture is of our team in our last weekend getaway. Our team is based in Uruguay, Argentina, and Colombia, but we are hiring all over LATAM. Our projects involve computer vision, predictive analytics, recommender engines, natural language processing, data engineering, and more. But since generative AI is so trendy right now, I wanted to share with you some of the projects we are working using this technology. So we started working with generative adversarial networks back in 2020. We were building an aging system for one of our clients. So basically, we needed to take a picture like the one of myself here and generate images of myself older or younger and that kind of stuff. After that, we actually extended that system to take into account other lifestyle effects, to apply other effects to the pictures, like what if you gain weight, or if you smoke and drink too much, how that will look like on your face, for example, and stuff like that. In this case, we started using style gun architecture. Some of you may remember this popular network built by NVIDIA. And the key feature of this architecture is that the generator has the ability to modify features or characteristics independently. So it does it in a highly decoupled way. So this means that we can modify, for example, the age of the face, but preserving the other characteristics. This means that we can preserve with these models the identity, preserve the identity of the person, and that was crucial for this project. So while developing this solution, we found that with StyleGAN we could generate high-quality images, actually, and in general it was good to preserve the identity. But we also, of course, find some issues. For example, to give you a couple of examples, when aging people, we noticed that glasses started to appear, for example, in the faces. Another example was that when we began to fatten up people, we noticed that Asian characteristics started to appear also, as we see in this example here. And also another problem or another characteristic of this StyleGAN architecture is that in general, the compute costs are high. So inference times and hardware costs are in general too high to put this into production sometimes. So to solve this, we actually use a technique that is called model distillation. So in this technique, we have a student network that is trained, that learns from the output of a larger teacher network that is already trained. So in our case, we use the StyleGAN as the teacher network. So we use it to generate different random faces, high-quality faces from that trained network, and also the corresponding, for example, faces with a modification. For example, let's say 10 years older, for instance. So with these pairs of images, we build a synthetic data set we later used to train this student network. So with this, the student network we used in this case was a pix-to-pix model. And by doing this, we actually improve a lot our system, and the inference times improve more than 150 times faster. So it was actually a great improvement. Of course, we need to still take care of the quality of the data set we generate with the StyleGAN model, because when generating the images, artifacts may appear on the images, or also bias problems, as I was mentioning just before. So we need to take that into account to eliminate images that do not correspond. So we have a blog post on this on this case. So if you want to look more details on this, you can look for that on our website. Another example I wanted to share with you is another project we are working on for a client. It's a virtual try-on solution. So in this case, we have an image of a person the reference image we see here in the picture. And we also have a picture of a garment, for example, a t-shirt, as we see here. And what we wanted to generate here is a fake image of how that t-shirt or that garment will look like on this person, as we see here. So for this, we are basing our work on this paper, Beton HD. You can look for it if you want to. And it's actually a complex architecture where we have different modules with different networks that perform different tasks. For example, we need to do some pre-processing to the image of the person to, for example, extract the pose, segment their body parts and their clothes, for example. We also need to do some geometric transformations to the garment we're going to use to do the try-on. With all of that, we generate another segmentation that is appropriate to the person and the garment we are using, and mixing all of these inputs, we generate the try-on, actually. So these are some results we are obtaining. So this is the original person, this is the real image. These are some intermediate results, for example, the pose, a segmentation, and also the t-shirt we are going to use to perform the try-on. And these are the results. It's the same person, but wearing a different t-shirt. So in this case, we are also adding another module that tries to understand how that t-shirt is going to fit on the person. So this is why we have an image generated with the try-on result with a t-shirt size medium and another one with size large, for example. So another thing I wanted to tell you is that for this same project, we are now trying and experimenting with some diffusion models. So in this case, for example, we are using an in-painting stable diffusion to try to improve the results of the try-on. So here we can see the try-on, and here the result with the try-on with the stable diffusion. So I don't know if you can see it here in too much detail, but the skin on the arm of this guy looks way more realistic, applying stable diffusion also, than the previous image. So we are experimenting with this, seeing how we can improve these results and complement the solution. So this was what I wanted to tell you today, so thank you very much for your attention.
Thank you very much, Paula. We have just time for one question.
Thanks for the talk. You showed us this awesome model and awesome results. I would like to know more about how did you acquire data? Was it provided by the contractor or something? Is it a challenge?
Yes, of course. It is a challenge indeed. Actually, we have our own small labeling team inside our company, and we're building this data set. We need a lot of data to obtain these results. Actually, we have a data set with over 100K images. So yes, it's a hard task, actually.
Thank you very much, Paula. And
Thank you.
Welcome now, Manu. Manu. So Manu Reinert is from IDATA. He's originally from Belgium, where he obtained his master's degree in business engineering in 2015. After working as a risk consultant at PricewaterhouseCoopers and Hedera Consulting, he moved to Uruguay in 2017. In Montevideo, he completed a postgraduate in big data analysis, and after that, he started working as a data scientist. Today, he works for IDATA where he is responsible for data engineering and machine learning projects for US clients. So we give a warm welcome to Manu.
Hi, everyone. First of all, thank you to everyone. Just a quick show of hands. Who here is from Uruguay and who is from outside? From Uruguay? Anyone from Europe? No one? Ah, there? Ah, okay. Nice. Okay, just checking. I'm going to present the data. I will try to keep it light and not go too technical already at the end of the day. I'm also going to talk a little bit more about who we are and less about what we do. But let's see if I can get this working. So we are eData, also data science company. We're 9 years old and we have around 35 team members, 30 of which are engineers. And within eData, very similar to Marvik from what I saw, we also do machine learning, natural language processing, computer vision. That is basically our machine learning department. And aside from that, we do data engineering. Data engineering for us can go from building big data ecosystems to simple ETL pipelines or even just some data visualizations. And on the other hand, within machine learning, lately we're doing quite a lot of causality. Because as you all know, machine learning is all about finding relationships and correlations, but that doesn't necessarily imply a causal relationship. Some of our clients, for example, financial institutions, they are legally obligated to give some kind of an explanation when, for example, they refuse to give you a loan. And that's where causality is really helping us today. Natural language processing, as an example, we're building a big search engine for a client, and we do a lot of computer vision projects both in LATAM and North America. So that's what we do, but who we are, and when I want to talk about who we are, I need to mention Pixies, because we are part of the Pixies ecosystem. Pixies ecosystem is basically our 10 technical units, all with their own speciality. So we, of course, data and AI, but there's also a technical unit that's focused on web development, mobile development, DevOps, there is one on cybersecurity, and so forth. What we do with Pixies is that we share all the same values, we share the same culture, and right now we're over 350 people. We have offices all over Latin America, one in Madrid and a small one in New York. Okay, and one of the things in our culture with Pixies is that we try to put people first. That's really one of the big things within Pixies, people first. And so we try to give a lot back to the community, to society, and we try to do that via our social impact projects. What are those? So we have Basura Zero, or Zero Garbage. And that's a project we started here in our office in Montevideo. We have around 80 people there. And we basically generate the equivalent of, a family of 4 in terms of waste. So it's a very little waste. We try to recycle everything. So that's one of the projects. Furthermore, we're also part of the UN Global Compact Board of Directors. And we started the Plus 50 program. Very interesting, actually, because we saw that in Uruguay, and I think in the rest of the world as well, for that matter, it's very difficult to find a job or to jump between jobs when you're above 50 years old. And on the other hand, we also saw that there's a lack of human resources or a lack of engineers within IT. So we basically try to solve one problem with the other. And right now it's a very successful program. We incorporated already quite some people above 50 within in Pixies. So we'll definitely try to keep investing in that. And then last, fibers or fibras. So that's an ecosystem, and that's not just Pixies, but it's anyone within Uruguay right now, and I think also Colombia, who is a tech company and willing to create a positive change, social impact, whether it's on education, on ethics, well-being, etc., but via technology. So should there be anyone also within here that wants to know more about this or wants to talk about this, maybe form part of it, definitely let us know, okay? And then very short, a small project, because of course the reason that we're able to invest so much and give back to society is because some of us still work and do these projects. So this is actually a pretty cool one that we did some time ago for a design agency. And one of their clients was a paint producer. And so what they wanted to accomplish was to build a user application where the user would be able to upload a picture of his or her interior, and then they would be able to select the walls and the ceiling, etc., and automatically recolor them, of course, with one of the paints of this paint producer, of this client. So what we did was, basically we started with a base model, and we found a data set around, I honestly can't see it, 25,000 images, and a lot of labeled data already. But one of those objects that was labeled were ceilings, were floors, were walls. So that was something that we could use. So after a couple of adaptations, we played around with the architecture, we did some transfer learning, I think we did a lot of data augmentation and added new data to it. We were able to go from 66% mean intersection over union to almost 85. So very cool project. Here is the final result on a picture that's not perfect. For example, you can see that there's a little bit of recoloring on the bench. There is the wall segment at the left that's not recolored. So it wasn't perfect, but it was client was really happy, and so are we. So that's basically us in a nutshell, who we are and what we do. Furthermore, we do play some football at times. We do a lot of asados. We hang out a lot with all of us, and yeah, that's basically it. This last picture is us in on our last event. So that's us. Thanks.
Thank you very much, Manu. We have for one question. Well, we thank you, Manu again. And that's our last sponsor talk. That Pablo Rodriguez works in Antel, our main telephonic company. Pablo is a full-time professor in the Institute of Computer Science here at the Facultad de Ingeniería, where he received 2 bachelor degrees, computer science and electrical engineer. He's also has also a master's degree in computer science. In 2008, he received his PhD in science from the University of Rennes in France. As principal data scientist, Pablo conducts research and development in products and services at the largest telecom company in Uruguay called Antel, mainly developing predictive and prescriptive models. Also, he co-founded 3 startups. Welcome, Pablo.
Okay. Thank you for the introduction. Thank you for the organizers for the hard work. I have 2 objectives in this last talk. The first, to give you an idea of what we are doing in Antel with IA. And the second objective is to present you a case, a demand forecasting case that we solved in the last year. So I don't know what is going on. Sorry. Okay. Oof. Okay. Antel is the largest telecom company in Uruguay, with millions of mobile and fiber services. It involves managing a large amount of data and a lot of analytical challenges. We organize our team with a central team with engineer and data science capabilities. This team who offer these capabilities to other parts of the company, in particular to data science and engineers at each department who act as a business experts and develop the analytical tools that they need. We have a lot of deployed infrastructure, mainly on-prem, with open properties software solution. Just to mention the most important one, we have a Cloudera big data platform as our data lake. We use Tableau and Cognos for visualization and data warehousing. We use the cloud mainly for heavy computation. We do it in Cluster UI, that is a national infrastructure for high performance computation that we share with the university and other companies. We also, of course, use Amazon and Google Cloud platform for a specific task. Okay, go ahead. In the last 20 years, we applied data science in order to improve our products and services. In the last 10 years, we systematically, great. Antel is everywhere. In the last year, we applied systematically data science in particular business cases. We manage a lot of descriptive information. We have more than 500 dashboards in Tableau and hundreds of cubes in Cognos. We have several deployed predictive models in production. We are developing proof of concepts for new problems every month. In production, we have recommendation system for devices, plans, entertainment. We have model of customer behavior for segmentation, churn, upsell, etc. We also assist the different business stakeholders with prescriptive analysis. We help network managers to optimally deploy new infrastructure and network design. We help network operators with anomaly detection, route failure analysis, these kind of things. We also assist the contact center, redirecting troubleshootings in order to improve their response time. And we also assist marketing people in the acquisition planning. That is the case that we choose to show to you today. So about the case, the demand forecasting problem, we have more than 150 stores across the country. Adding the online sales, we sell more than 30,000 high-touch products per month, mainly mobile phones. The order fulfillment is characterized by a very long time period because we order large quantity products in manufacturer countries in China, and it takes more than 3 months to have the products, the items in the store. So you must think a little bit about that because it's very important to do it efficiently, not just because that is involve a lot of money, just because also there is a potential risk of stock out. So we decided to help the marketing people developing a demand forecasting model to predict the accumulated demand for each product for the following 121 days, the following 4 months. In the picture, you can see a typical life cycle demand of a mobile phone. The blue line is the demand, and you can see that it starts with a fast growth at the beginning, and in some point, the sales start to decrease for several reasons. Mainly, it doesn't work, no? Oh, yeah. For several reasons, mainly because a substitutive product appeared in the market. I think that in this case, it happened 2 times. Here in 2020, at the beginning of 2020, here at the end of 2020. Oh. It's a hard problem to solve, this demand forecasting, not just because of the long forecasting period, but because of it was very complicated to create a representative data set, because several reasons that appear there, and because the cold start problem is very clear in this case, because we introduce new products every month. So we decided to solve it in a traditional way with supervised machine learning. We created a data set with 300,000 samples in training and the same in testing. We used RMCE to compute the quality. We tried several models, from time series forecasting models to transformers models. We choose to use LightGBM, a popular gradient boosting machine framework developed by Microsoft people. The hardest part of that was the feature engineer. We computed more than 500 features, and the model currently is using 28 features. We also fine-tuned the hyperparameters with Optuna. We had no troubles with that. The business stakeholders recognize a value in the prediction, and marketing people is using the prediction in order to define the new acquisitions. In average, we have a 1,000 error in RMS. You can see in the picture that the orange prediction follow in some way the blue real demand, including in particular case that this one, that in the iPhone 7 we restart to sell as a short promotion in 2020, and the model understood that quite well. So to finish, just a little bit about the product. We use a set of dashboards in Tableau for the front end, and in the back end, we perform a daily prediction. With Spark, we compute the features, and monthly we retrain the model with fresh data, do some sanity check, and deploy the model. It takes approximately 5 hours in our cluster of servers, and that's all. Thank you for your time. Thank you for your attention. And I am here if you want to discuss more about the challenges of IA in the telco industry. So thank you.
Thank you. If there is any question, we can have one question, and Enzo will show a slide about the day of tomorrow with some information. Is there any question for Pablo?
Hi, also presentation, it was really interesting.
Thank you.
The question I had was if you managed to find a way to deal with the cold start problem. We had a similar problem at Trio where we worked, where we had items that were sold only once, so that was kind of the most extreme case of cold start. And the way we worked around that was by having features that the model could use to extrapolate past sales from other items that were similar to the ones that we were selling, and that worked pretty well. But I was wondering what was your experience?
Okay, yes. In essential is what we did. We use only one model for all the products, and we use it as features, things like similar that you say. For example, model from the same brand usually are selling, I don't know, some number, or also the fast curve at the beginning in the sales. We have a different curve for each brand, so this is a feature also. So we have a lot of features about similar items in the data set. Yes, we did it a lot. We also have another trick because we know which models, which products are in the network. So we take also information about, in some way, of the market, what is going on in the market, and we can anticipate what will going on with ourselves from that. But in essential, the set of features follow the idea that you mentioned. Thank you.
Cool. Very interesting. Thank you.
Thanks, Pablo.
Okay, so this was our last talk for today. A couple of announcements. We have now the tutorials. So we have 3 different tutorials. These are the rooms. All the rooms are in the Faculty of Engineering building, the other building. Okay, so I think they are correct today. They are also in the website. And before you leave, tomorrow we will start with the parallel sessions. So parallel sessions are going to be round tables with various speakers in every one of these parallel sessions, talks about 20 minutes each. I invite you because these are going to be really, really interesting talks, so don't miss them. Some of the speakers are here, some of them have been here in the research talks. I mean, it's a mix, it's really interesting. And we'll have 2 in the morning, 8:30. Please try to be on time because we are starting with a lot of delay. Computer vision is going to be in C22. This is upstairs, in this building, upstairs. And natural language processing is going to be here in the main auditorium. Then we will have ethics and social impacts in AI here in the main auditorium, and reinforcement learning in upstairs. And well, tomorrow we continue with great also research talks, and at the evening we will have the Women in AI event that we will then let you know what are the logistics to get to the place. But this, we will talk about that tomorrow. Thank you.